Building a concurrent system in Java requires a rigorous understanding of thread life cycles, memory boundaries, and deadlocks, far beyond simply spinning up an executor service. Critical production outages almost always trace back to subtle mechanical misunderstandings of how the Java virtual machine manages state under load. We are focusing on three specific failure vectors: orphaned thread states, hidden memory leaks in worker pools, and data loss during system termination. This deconstruction will ignore elementary analogies in favor of the architectural trade-offs and edge case failure modes that actually break high-throughput systems. By systematically breaking down these traps, we can reveal the specific design patterns required to achieve genuine fault tolerance. Mastering these critical edge cases is the technical threshold that separates merely writing syntax from architecting high-performance systems. Forcefully killing a thread using legacy stop commands is an immediate hazard to system health. A forceful termination can leave shared monitors locked and critical system resources unreleased, leading to silent deadlocks and resource exhaustion. Resilient systems rely on two-phase termination, a cooperative shutdown pattern where threads are designed to exit based on internal state checks. Relying on a volatile Boolean alone is a mechanical failure. As this map shows, a thread in a waiting block cannot check it. You must combine it with an interrupt command, triggering an exception that mechanically forces the thread back to the ready loop. Once awakened, the thread catches the exception, checks the termination flag, and executes its final cleanup logic before exiting gracefully. Scaling this logic to entire thread pools requires a tiered architectural approach to shutdown. Production best practices dictate a smooth followed by forceful sequence. Call shutdown, wait for completion, and only fall back to shutdown now if the timeout expires. Predictable thread termination is a mechanical requirement for maintaining system stability and data integrity. Defaulting to synchronized blocks for all shared state creates lock contention, which throttles your system's throughput. High-performance systems bypass this through zero-sharing architectures, such as the copy-on-write pattern for read-heavy workloads. In this model, reads are completely lock-free. When a change is required, the entire array is duplicated, updated, and the reference is swapped. Despite the memory cost of copying, this provides the low-latency reads required for critical infrastructure like RPC routing tables. Thread local storage offers another zero-sharing path by isolating state variables entirely within individual threads. However, using thread local inside an executor service without lifecycle management leads to a fatal memory leak. Because thread pools reuse threads, the thread local map remains alive even after a specific task is finished. This orphan data results in cumulative memory leaks and risks data contamination when the thread picks up its next, unrelated task. To prevent this, you must always call tl.remove inside a finally block to scrub the map before task completion. Zero-sharing designs will optimize your concurrent performance only when the developer meticulously manages the complete lifecycle of that isolated memory. Systems fail when threads blindly execute redundant logic, or when subsystems with different processing speeds are tightly coupled. The bulking pattern provides a fail-fast control flow, immediately aborting execution if a prerequisite condition is already met. This pattern prevents wasted CPU cycles during scenarios like double-checked locking or saves for files that haven't changed. Bulking logic fails if the initial check and the subsequent state change are not executed as a single atomic operation. At an architectural level, we manage back pressure and decoupling through producer-consumer queues. Replacing the unmanageable thread per message model with a bounded queue between task submission and execution creates a vital buffer. This architecture provides subsystem decoupling, completely eliminates thread creation overhead, and serves as a primary shock absorber for the entire application. During traffic spikes, the queue catches the excess load, protecting the downstream system from an immediate crash. This graph illustrates peak load absorption. A fixed worker pool steadily processes this backlog, allowing the system to survive surges that would otherwise cause total collapse. Queues protect the system from collapse by converting unmanageable traffic spikes into a steady stream of deferred work. Mastering high concurrency depends on an engineering-level understanding of the mechanical realities within the JVM. Resilient architecture is built on cooperative, interrupt-driven thread life cycles using the two-phase termination pattern. It requires sidestepping lock contention through zero-sharing designs while vigilantly managing thread local memory boundaries. Finally, it demands that we decouple execution through fail-fast bulking logic and producer-consumer buffers to protect absolute system capacity. Internalizing these patterns allows you to stop fighting the thread scheduler and start architecting truly fault-tolerant systems.